The M drive is claimed, it was first introduced back in 2001. It's been claimed to be a revolution in propulsion. Like every kind of rocket we have requires a propellant. You got to push something out the back end in order to make your rocket go forward. Whatever it is, doesn't matter. It can be exhaust from a fuel. It can be a bunch of electrons or ions. It could be bouncing a laser off of it. It doesn't matter. In fact, that's how all of motion is. Like if I want to move forward, I need to push off the earth. If I want my car to go, the tires need to push off the ground. That's how motion works. And we understand this through the conservation of momentum, which I talked about in the last video at length. But in the years since the introduction of the M drive concept, which is where you just have a box of microwaves in a specially designed cavity, and it's perfectly enclosed, nothing leaks out, but then somehow this generates momentum and thrust, violates conservation of momentum, which isn't going to fly. Literally. And or like some groups claim, like there's various groups around the world that are trying to get this to work. I don't know why. I think they're wasting their time, but that's just me. Because you can say like, oh, Paul, you're just a dinosaur. You're not, mind isn't open. Aren't you ready for physics to have a revolution? Like, yeah, I'm ready for physics to have a revolution. It's not coming from that. It's not coming from the M drive. And it's because the experiments are all junk, and that's what I'm describing today. But there have been various explanations for how it could work. Like maybe it pushes off the vacuum energy, and it just turns into mumbo jumbo. Like literal nonsense, like the non-physics, just taking physics words from Wikipedia and stringing them together and crossing your fingers. That's not how physics is done. But there have been various experiments purporting to show or attempting to show that an M drive could work. And some of them have made claims that say, yes, we see a thrust that is greater than our statistical uncertainty. We have a good significance of a result. We are seeing a measurement here. First off, we're talking thrusts so tiny they couldn't even push a piece of paper. That take months, multiple experiments to get any sort of significant source of data to make any sort of conclusion whatsoever. And every once in a while, like every few years, a paper comes out like claiming to have measured a thrust. Or what usually happens is a group will claim to have measure a thrust, but not actually publish. But sometimes they do. Rarely they do. And then I think the last big one was like in 2016 or 2017. The results are just not impressive. Not impressive. There's huge uncertainties in measuring the thrust because you've got like a box and there's all sorts of things happening, especially when you're trying to measure these very, very tiny thrusts, these very, very tiny forces. Like you walk by the thing and it shakes it. Or like there's like a weird electrical hum and that's enough to mess up the results. So these have to be very carefully controlled, very exquisite tests. You have to understand your uncertainties, all the potential sources of uncertainty. And there's two kinds of uncertainties. There's statistical uncertainty and systematic uncertainty. Statistical uncertainty is when you only have a limited amount of data. So your conclusions can only be so strong. And if you had more data, you'd be more sure about your answer. That's statistical uncertainty. And the solution to statistical uncertainty is just keep cranking, just work your experiment longer and longer. The other side is systematic uncertainty. These are the things that are introducing effects into your result that you don't want. Like you want to like turn on this box, an M drive, and then have it nudge around your little spacecraft, your test box, and measure the force. But there's like 1,000 other things that can also produce a measurable force, and those will introduce a source of uncertainty. That's your systematic error. All the papers I've read about M drives do not do a good job at estimating their own uncertainties. The statistical significance of the results are weak. Like yeah, we got it. Here we did. We measured this thrust. But then you look at the error bars and how big the uncertainties are, and then you know that those aren't even close to what the true uncertainties are because they haven't talked about what all the sources of uncertainty could be. And even then, just taking the stated uncertainties at face value, there's like no measurement. There's no measurement. Like if I were the referee of those papers, I would say you don't have a result. All you've done is measure noise. Still, you can take that. You can take these published results at face value and say, okay, weak marginal result at best. Now I'm going to go replicate it. And attempts have been made to replicate some of these published mDrive results. The replications either end up getting no measurement whatsoever, or find some other source of systematic uncertainty that the original experimenters didn't think of. In one famous case I remember, there was an experiment on the mDrive and they realized that, yes, they saw a measured thrust. They were able to see a statistically significant thrust from the mDrive, but they were able to account for it due to the interaction of the cabling with the Earth's magnetic field. Like that's how tiny of an effect we're looking at, and you have to take care of it. And then once you account for that, the effect goes away. So people have been trying to make an mDrive work for 20 years, and they haven't gotten it to work for at least 20 years. In the experiments that I've read about, the ones that are actually published, from my view as a scientist, the papers are poorly presented. The statistics are not well understood. These things are not rigorously controlled. They are just like bad, like not necessarily bad experiments because they're trying and they're not trying to deceive, at least on the surface, because there's also this case of cherry picking where, you run experiments for 6 months and then a couple of them look really, really nice. So you just pull those and just publish that. And that's also another reason, like there were these large, I remember this like 2016, 2017 paper, these large statistical uncertainties that just made the results like meaningless, statistically meaningless. I'm like, if you really thought you were onto something, why didn't you just run this thing for 2 more months so you can shrink those error bars down a bit? Makes you wonder why you stopped there. Anyway, am I ranting? I think I'm ranting. I'm not convinced by the mDrive. I honestly think it's a waste of time. There is no known physics that could possibly explain how it works. You either have to violate conservation momentum or you have to make up new physics. And the experimental results have been less than stellar. Not nearly convincing. I don't know. And that's what we got. It's been 20 years. When are we going to give this up? And do something else with our time. I don't know. See you next week. I hope you like, share, and subscribe. And I hope you go to patreon.com/pmstarter to learn how you can keep this show going. And I'll see you next week.